In this video, we're going to talk about operations with functions, which just means we're going to take at least two functions, if not two, three, or four, and we're going to perform different operations with them. So operations being adding, subtracting, multiplying, and dividing. There are a few different ways that we can show what operation we're using. And in all of them, we're going to use function notation. So just a little reminder that function notation is just a way for us to name a function so we know exactly which function we're looking at. So you're going to see names like f of x, g of x, h of x, k of x, j of x. That f, g, h, k, j, they are all just a way for us to give a name to a function so that we know which one to look at. The same way your parents gave you and your siblings different names so that when they say a name, you know exactly which person they're talking to. We have given each equation a different name so that we know exactly which equation we're looking at. That just makes it easier than if they all said y equals. You wouldn't know exactly which equation I was looking at. So that's the point of f of x, g of x, h of x, all of those. But there are a couple different ways that the names, the notation itself can be set up. So for addition, we could see it as f plus g of x. And this x at the end, that can be kind of confusing. This isn't my favorite notation because of that. It looks like we're multiplying by x here. It looks like we're adding f plus g, but then we're multiplying by x. That is not what is happening. That x at the end just tells us that there is going to be an x in our equation. So another way to write this that I think is a little clearer to see is to have f of x plus g of x, where we can explicitly see that x is going to be in f and it's going to be in g. And I think that's a little bit easier because if we just look at an example, like from this first one, f of x equals 3x plus 8, we can see exactly what f of x is equal to. We know that that 3x plus 8 is going to be plugged in for f of x. Whereas with f plus g, and then having that x at the end, it can be kind of confusing. But all that means is that there will be an x in our answer. Same idea for subtraction. Now we're just switching out our operation. So f minus g of x. Again, that x, we're not multiplying by x. It just means there will be an x in the answer. And a clearer way to write that is f of x minus g of x, where we can clearly see what we're doing with our two functions. And then similarly as well is multiplication. Again, just switching out our operation. We have a multiplication dot there, so f times g of x, where x is just in our answer. We are not multiplying by x. And then clearer, f of x times g of x. So that tells us that we're just multiplying those two things together. When we multiply functions, a lot of times this means we're going to be foiling out our answers or distributing in some form. That did not come up in the first two. With addition and subtraction, this just means we're combining like terms. So all that means is that we are looking for terms that have the same variable with the same exponent, and then we're adding or subtracting their coefficients together. With multiplication, we're going to FOIL, so we're going to be multiplying their coefficients and adding their exponents. And then lastly with division, so in this video and in this section, we're going to keep division pretty simple. We're not going to be giving you any functions that can be simplified or reduced in any way. You will just be taking two functions and dividing them, so just basically plugging them into the fraction. That's all you've got to worry about here. So f divided by g of x, again that of x just means that there is going to be an x in our answer. And then a better way to write that is f of x divided by g of x, so just the fraction of those two functions. Once you, on division problems, once you plug it into the fraction, that's it. You don't have to simplify any further. Once we get into rational functions later in the year, that's when we'll worry about simplifying and seeing if we can cancel anything or reduce or whatever. Now with division, when we're talking about functions, we do have to be careful with our denominator. In this case, g of x is in the denominator. And because we're dividing, that means we're talking about fractions. And if you think back to when you learned about fractions sometime in elementary school, we cannot have 0 in the denominator of a fraction. We cannot divide by 0. 0 in the denominator doesn't exist. Gives us a black hole. So we are going to have to pay attention to any x values that make that denominator 0, because we're going to have to exclude them from our domain. We're going to have to note in some way that those x values cannot exist. All right, as well as talking about operations of functions, we're going to be talking about the domain of our answers as well. So let's define that a little bit. We know the domain of a function is the set of x values that make up that function. So the domain of the results of the different function operations are going to be the x values that are in the domains of both functions that we are performing the operations with. So f of x and g of x, it could be g and h and j, k and f, whatever it is. However, we do have to be careful when we divide two functions. So for example, f of x divided by g of x. In that case, we do have to exclude any x values that cause the denominator to equal 0. Just like I briefly talked about above with division, we cannot divide by 0. So if we're talking about the domain of any of these functions or the result of any of these operations, we do have to consider any x values that might make that denominator 0, and we have to exclude them. So we have to indicate somehow that those x values cannot be part of our domain. So we'll see that when we get to some division practice. So first up in example 1, we're just going to be looking at addition and subtraction. So first I want to perform the actual operations, then we'll go back and we'll talk about the domain of each of these answers. So starting with h of x, they tell us h of x is equal to f plus g of x. So remember I said I don't love this notation because that of x at the end can be kind of confusing. So I do want to rewrite this. This is the same thing as f of x plus g of x, where we are just adding those two functions together. And I think that's a little easier to see exactly what we're doing. So let's set up our problem. H of x is equal to f of x plus g of x. So we're going to start by plugging in f of x. And anytime I plug something into an equation, I always like to plug it in with parentheses first, and then we can go back and simplify those parentheses out of the problem. But if we start with parentheses, that helps us see exactly what needs to be grouped together, and then if anything applies to those parentheses, it helps us to remember that we need to distribute it to both of those terms so that we don't forget a sign or multiplication or something like that. So we have f of x plus g of x, which again I'm going to plug in with parentheses, and now we can go ahead and simplify. Now we are just adding these together, we're not distributing anything to the second parentheses. I guess we are distributing a positive 1, there's an invisible 1 there, but when we distribute positive 1 it doesn't change anything, so in this case we are able to just get rid of those parentheses. But if we were subtracting anything or we had a coefficient that we needed to multiply, we would need to distribute those things first, and then we could get rid of the parentheses. So now we can combine like terms, starting with our x values. 3x plus 2x gives us 5x, and then our constant terms, we have 8 minus 12, which gives us negative 4. So that tells us h of x is equal to 5x minus 4. We'll come back in a second and we'll talk about the domain, but we're going to go ahead and move on to part B, and we'll come back. So this time we're talking about k of x. So k of x is equal to 2 times f of x minus g of x. And they've given this problem to us in a way that I think is a little bit easier to see. So we're not going to rewrite anything, we're just going to start plugging things in. So k of x is equal to 2 times f of x. So I'm going to have 2, and then in parentheses I'm going to plug in 3x plus 8, and then we are subtracting g of x. So we're subtracting 2x minus 12, and especially when you're subtracting, putting that second function in parentheses is super important. Like you're going to make a mistake if you don't put that second one in parentheses. And the reason why is because we're subtracting both terms in that second function. So we're distributing that negative to both of those terms, and parentheses remind us that that distribution needs to happen. Same thing with the first function in this case, that 2 gets distributed to both the 3x and the 8. If we forget to put that 3x plus 8 in parentheses, we might forget to multiply the 2 times the 8 as well. So those parentheses really help us to remember to distribute anything in our problem. So in this case, we'll distribute that 2 to get 6x plus 16, and then we'll distribute the negative so that we get negative 2x, and then negative 12 becomes positive 12. And then we'll finish up with combining like terms. So 6x minus 2x gives us 4x. And then our constants, 16 plus 12 gives us 28. So that k of x is equal to 4x plus 28. So we have performed our operations for both examples. Now let's go back and talk about their domains. So for our domains, like our definition said, we have to consider the domains of both of the original functions. So if we look at our original functions, f of x and g of x, 3x plus 8 is just a line, and we know lines have a domain, which I'm going to abbreviate with d, of negative infinity to infinity. And then g of x is equal to 2x minus 12, which is also a line, so that domain is also negative infinity to infinity. Both of the operations we performed, addition and subtraction, we didn't end up with a fraction or a variable in the denominator, so we don't have to worry about excluded values. So we are just looking to see, where these two domains overlap. So where negative infinity to infinity and negative infinity to infinity overlap each other, and since they're the exact same, they overlap each other everywhere. So the domain for each of these is also going to be negative infinity to infinity. If we had any like weird functions like square roots or rationals where our domain is bounded in some way, then we would have to consider that for our answer as well. But since these are both continuous functions, we resulted in a continuous function as well. All right, so that was addition and subtraction. Let's try it with multiplication and division. And again, we're going to perform our operations first, then we'll go back and talk about their domains. So let's start with part A. So h of x is equal to f times g of x. Because that notation's kind of funky, let's rewrite this. So really this is f of x times g of x. And like we talked about earlier, anytime we're multiplying, we're going to have to FOIL or distribute in some way. So let's plug in our functions. So h of x is going to be equal to f of x, which is x squared minus 1, times g of x, which is x plus 5. And then to simplify, we're going to FOIL it. You might prefer box method, which is fine, or you might just prefer, instead of thinking about it as FOIL, just distributing. Those are the same thing. Whichever method you prefer, that's what I want you to do here. I'm going to FOIL it out. So first times first, x squared times x is going to give us x cubed. Then x squared times 5 is 5x squared. And then negative 1 times x is negative 1x, or just negative x. And negative 1 times positive 5 gives us negative 5. And then we would go back and combine any like terms if we could, but each of these terms has a different exponent on it, so none of them are like terms, so we have simplified as much as possible. So that means h of x is equal to x cubed plus 5x minus x minus 5. All right, moving on to part B. This time we're dividing our two functions. So like I mentioned at the beginning, when we are dividing in this unit, we are literally just plugging into that fraction, and there's not going to be any more simplifying you can do. We have set it up so that no simplifying needs to occur. They've given this problem to us in a way that's easy for us to read. So f of x divided by g of x, we're just going to plug our functions into that fraction. So f of x being x squared minus 1 going in the numerator, and then g of x being x plus 5 going in the denominator. And that's it. We're just plugging in. There's nothing else we can do in this unit. Now that we have performed operations, let's go back and talk about our domains. So we're going to identify the domain of each of our original functions first. So f of x equals x squared minus 1. That's a quadratic, that's a parabola, and parabolas have a domain of all real numbers, so negative infinity to infinity. And g of x is the equation x plus 5. That's a line, and like we talked about before, all lines have a domain of negative infinity to infinity. So these domains are the exact same, which means as long as we did not divide in our problem, our domain is going to be negative infinity to infinity, and that we ended up with a continuous function. So h of x, we did not divide. A cubic function is continuous, so our domain will still be negative infinity to infinity. And then part B, k of x, we did divide this time. So we need to pay attention to what's going to make this denominator equal to 0. So we know we cannot divide by 0, so that means x plus 5 cannot be equal to 0. So we want to get x by itself to figure out what x cannot be. So I'm going to subtract that 5. And that tells me that x cannot equal negative 5. It can be anything else, literally any other number, but it cannot be negative 5. So we're going to have to break up this domain of negative infinity to infinity, and we're going to have to stop it at negative 5, and then we can let it continue on the other side of negative 5. So the way we're going to write this, we're still going to start at negative infinity, but we've got to stop at negative 5. Since our domain cannot equal negative 5, we're going to put a parenthesis around that negative 5 to indicate that it cannot be equal to negative 5. And then we're going to pick back up on the other side of negative 5. So this means our graph is going to get infinitely close to negative 5, it's just not going to touch it. And then on the other side, it's going to get infinitely close to negative 5, it's just not going to touch it. So we're going to use a union to show that there's another piece to our graph that's going to start at negative 5 on the other side, and then it will continue off to infinity. So anytime we have divided, just pay attention to what x cannot be, and that is just that's where you're going to break up your domain, right there. So division's a little bit weird. All right, so to finish out this section of notes, I want you to practice a little bit on your own. So I want you to write these problems down, I want you to pause the video, and I want you to work through them. And then once you have worked through them, come back and look at the answers to make sure that you got the right answer, that you did your work correctly. I will provide solutions here so you can watch through them in case you did not understand it or you got the wrong answer. But take this time to practice on your own. So pause it, work it out, come back when you're done. All right, now that you're back, you've worked all of them out, right? You didn't just wait for me to talk again. Let's go through these 4 examples quickly. So part A, we are adding f plus g. So f is 3x minus 1. And we are adding 2x squared minus 3. We talked about before, if we are adding, as long as there's nothing to distribute, we can go ahead and get rid of our parentheses. And then to finish out, we're going to combine like terms. When we write our final answer, make sure to put them in order, starting with the biggest exponent and working your way down. So that means we're going to start with 2x squared, then we'll move to 3x, and then we'll finish out with our constant terms, but we're going to go ahead and combine those together to make that a -4. So that would be our final answer here. At the end, I'm going to go back and write the domain for each of these. All right, so in the middle here we have f minus h of x. I'm going to rewrite that because we don't like that notation. So f of x minus h of x. So that tells us that we have 3x minus 1 minus 7x. Now with subtraction, we talked about those parentheses are really important because that subtraction sign applies to everything that follows it. So this becomes 3x minus 1 minus 7x. And now we can combine like terms. So starting with those x's, 3x minus 7x gives us -4x minus 1. And that is our most simplified answer for f minus h of x. Okay, then part C, we have g of x times h of x. So g of x being 2x squared minus 3, h of x being 7x. And remember with multiplication, this means we're going to have to FOIL or distribute. So we're going to distribute that 2x squared. So 2 times 7 is 14, x squared times x is x cubed. And then -3 times 7x, -3 times 7 is -21. And then that x will just stay the same since it doesn't have another x to multiply by. These are not like terms. They have different exponents, so that's our final answer. 14x cubed minus 21x. All right, lastly, part D, g divided by f of x. We talked about rewriting this just so it's a little easier to see. So this is g of x divided by f of x. And we talked about in a fraction, in this unit, we are literally just plugging it in. We're not simplifying anything else. So g of x is 2x squared, not cubed, minus 3 over f of x, which is 3x minus 1. And there's no simplifying we can do. That's our answer. Now, let's go back and talk about the domains. So let's start by finding the domain of each of our original functions. Sorry, please excuse the beeping in the background. F of x, 3x minus 1 is just a line. So this has a domain of -infinity to infinity. G of x, 2x squared minus 3, that's a parabola. So this is also a domain of -infinity to infinity. And then lastly, h of x is just equal to 7x. That's a line, so it also has a domain of -infinity to infinity. Now, because for the first three, we have a quadratic, so that's a continuous graph. We have a line, that's a continuous graph. We have a cubic, that's also continuous. So because the original functions were all continuous and our answers are all continuous, these domains will all be -infinity to infinity. It's only the last one we need to worry about because we had to divide. So we do need to pay attention to what's going to make that denominator 0. So we know that the denominator cannot equal 0, so that means 3x minus 1 cannot equal 0. So now we're going to solve for x. So that means 3x cannot equal 1. We'll divide by 3, which means x cannot be equal to 1/3. So that 1/3 is where we're going to stop our domain. We're still going to start it at -infinity. It's still going to continue to positive infinity, but in the middle there, we're going to stop it at 1/3. So this is going to be -infinity to 1/3. We can't touch 1/3 because it can't be equal to 1/3, so we're going to put parentheses around it. And then we'll pick back up on the other side of 1/3, and we'll continue to positive infinity. So when you are performing operations and you're asked to find the domain, find the original domains first. Make sure they agree with your answers. They're also, in this case, continuous. But if you have divided, or if you end up with a variable in the denominator, figure out what makes that denominator 0, and that's where you need to stop your domain if that were to occur. So that's why we stop our domain there at 1/3 in the middle, and then it can exist everywhere else. So that is it for function operations.